Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
So I'm very pleased to introduce Haipeng Luo. Haipeng got his undergraduate degree at Peking University and then came to Princeton for graduate school, and the guy ended up working with me as his advisor. So he's done internships at AT&T and Yahoo and here. I'm not sure anywhere else. What? Two best paper awards this year, ICML and DIPS.
Great.
Take it away.
Thanks. So I'm Haipan. So my last name is actually pronounced as Law, Law as in LAW.
Now, when do you think your advisor would know that by now?
Actually, I have never told you about this. I mean, and it's 5 years, so it's about time. Anyway, yes. So I'm going to talk about online learning today. So online learning is about making a sequence of accurate predictions when interacting with the environment. So let me give you a few examples. So think about spam detection. So every day we receive a lot of emails that comes one by one to our account, and the spam detector needs to make a prediction on each of them, whether it's a spam or not. And after that, it sometimes get feedback from the users. For example, we can point out that an email in our regular inbox it's actually a spam, or the other way around. And based on this feedback, the spam detector somehow improve its strategy and hopefully make a better prediction next time. So this is one example of online learning. And the second example is about online routing. So imagine there's a network, and you have a bunch of packages to send from node A to node B, and they arrive one by one in an online fashion. So and for each of them, you pick a path in this network and send it. And afterward, you observe the latencies of this path. And based on this, you know something more about this network, and you adjust your strategy and hopefully pick a better path next time. So the last example is a recommendation system. So every time we visit Netflix or Amazon, a set of movies or products are recommended to us. And based on whether we click on these recommendations or not, the system will learn more about our preferences and hopefully make better recommendation next time. So these are all examples of online learning. And as you can see, it's a very general model that captures a lot of real-life applications. So the things, why is this model interesting? So in machine learning, a more traditional setting is the batch setting, where you have a batch of training data beforehand, and having this data, you can apply to any batch algorithm that you want, and finally you get a fixed predictor that you use for future prediction. But the advantage of moving to online learning is the following. So first of all, it's just a more natural model for many applications. So it's kind of missing the training and testing, and it can improve over time, and which is what we want in practice. And more importantly, it's memory efficient. It only needs one path of data. So we talk about big data these days, and when you have a huge amount of data, you just can't fit all of them in your memory. And now online learning is especially useful in this case, because for each data point, you learn something about it, and then you throw it away. You never really store it in your memory. Okay. And third, online learning is often distributional assumption free, meaning that we don't make any assumption on how the data is generated. While in the batch setting, usually we assume the data is generated from a fixed but unknown distribution. And because of this assumption-free property, is also online learning is also suitable for changing or even adversarial environment. So the data can be generated in any way, even in an adversarial way. Okay, so so these are the advantages of online learning, and it has been a very active research area in recent years, and has also proven extremely useful in practice. Okay, so the main goals of my work is, in a word, to design better online learning algorithms. So concretely, I want the algorithm to have the following properties. First, it has to be computationally efficient, and second, it has to be theoretically optimal in terms of performance. And third, it also needs to be adaptive and robust so that it works for different kind of data and also under different kind of criteria. For example, I might want my algorithm to have much better performance when the data is easy, when there's a clear pattern in the data, but still want to ensure that the algorithm is doing the right thing in the worst case. And finally, I also want the algorithm to be parameter-free or has as few parameters as possible, so that they are ready to use in practice. So you don't need to tune the parameters. Okay, and yes, so by better online learning algorithm, I mean algorithm that has all these properties. So with this goal in mind, this is the overview of my work. So, for example, this line of work is on how to combine expert advice when making these online predictions, and I will make more examples later on. But this is actually one of the most fundamental problem in online learning, and we have proposed a new adaptive algorithm to it. And besides this, I'm also interested in the intersection of online learning and other area. Like in this work, online boosting is about combining online learning and the theory of boosting, which is well known and in the batch setting is highly useful for machine learning. And we basically combine these two and propose some adaptive online boosting algorithms. And another direction is on applying data sketching techniques to online learning. This work is actually done in this lab. And basically, we applied data sketching, which have been proven useful in many other areas, to online learning to get some efficient online learning algorithm. So other examples include the connection with online learning and optimization, stochastic learning, and also game theory. So today I'm going to talk mostly focus on the first two, and if time permits, I will briefly mention the third one. Okay. So now let me start from online boosting. So this is joint work with Alina Begalzima and Sayan Kell at Yahoo. So here's a brief introduction of boosting. So boosting is a highly successful batch learning algorithm invented by Rob and Yoav Front. And the idea of boosting is to combine weak rules of thumb to form a highly accurate predictor. So let's go back to the spam detection example. So, but now imagine that you are in a batch setting where you're given a set of training examples. Each of them consists of an email and a label. So for instance, here the first email, want to make fast money, is labeled as spam. And the second one, how's your season going, from Rob, is not spam.
The second is not spam only before you graduate.
Yeah, exactly. Anyway, so what boosting does is to ask something called a weak learning algorithm, which can be any algorithm that you have, to get a classifier. So and this classifier can be something very simple. For example, it can predict spam as long as the email contains the word money. So it's very simple. It's not so accurate, but you do expect that it's better than doing random guessing. Okay, so then what boosting does next is to somehow reweight these examples so that those difficult ones get more attention. For example, emails, a spam that doesn't contain the word money will be considered as difficult ones here. Okay, and now having this reweighted batch of examples, boosting will ask the same weak learning algorithm again to obtain another classifier. And for example, this time it might predict spam as long as the email has no two edges. Okay, and so on and so forth. So at the end, boosting will output the majority vote, or more generally, the weighted majority vote of all these simple classifiers. And the theory of boosting says that as long as these simple classifiers is doing a little bit better than random guessing, at the end, my final classifier will be highly accurate. So this is the high-level idea of boosting. But so it's well studied in the batch setting where you have a batch of examples beforehand. But after all, it's a batch algorithm. It has the disadvantage that other batch algorithm has. For example, it becomes infeasible when the amount of data is huge, when you cannot fit all the data in your memory. So one solution to this is just to move to the online learning setting. And just to remind you, online learning is usually memory efficient, and it works even in an adversarial environment, which is kind of perfect for this spam detection application. And this leads to the main question of our work. How can we extend the theory of boosting to online learning setting? Yes?
With those two features of online learning,
Yes.
and are they kind of orthogonal, or do they go together naturally? Why, can you study? Can you study things that are adversarial but not, but in a batch setting?
I think so. I think they are orthogonal. They are two different things.
Two different.
Yes.
Okay. But they tend to go together.
Yeah, for online learning, yes. Okay. And just put it differently, we are asking how can we boost the accuracies of any existing online learning algorithms? This is what we try to answer. And we are not the first one to ask this question. There are several algorithms, several online boosting algorithms, but most of them just try to mimic the batch counterparts, and they do not have theoretical guarantees. Except for this work by Chen et al. A few years ago. Basically, they connect online boosting to batch boosting that produce a smooth weighting batch examples. And they somehow prove some guarantees for those algorithms. But we want to take one step ahead, and we want to try to figure out what's the most natural definition for online boosting. And on top of it, we propose two algorithms. One is optimal, and the other is adaptive. Okay, so now I'm going to tell you what our definition of online boosting is. So let me just again go back to the batch boosting and show you the formal definition. So again, you are given a batch of T examples. XT, think about it as the email, and YT as the binary label, spam or not. Okay, and a learning algorithm predicts A of XT as the label for example XT. So this learning algorithm A is said to be a weak learner, which adds gamma if the following happens. Basically, the number of mistakes formally written here is bounded by T times 1/2 minus gamma. So what does it mean? So it is saying that if you divide both sides by T, it's saying that the error rate of your algorithm is at most 1/2 minus gamma. And remember, this is a binary problem. So if you do random guessing, your error rate is 1/2. And now I'm requiring this algorithm to have just gamma better than random guessing. And think about gamma as something very small, as a constant that's very small. Okay? And a strong learner A prime is an algorithm that can have an error rate at most epsilon for any target error rate. So it can be as accurate as you want. And the theory of boosting basically says that if you give me a weak learning algorithm A, then by using several copies of it, I can construct a strong learner A prime. Okay, so this is what happened in the batch setting. And now let's move to the online setting. So remember now the example XTYT, they arrive online one by one. And they do not come from any distribution. And the learning algorithm first observes XT, and then predict the label A of xt. And after that, the environment reveals the true label yt. Okay. Okay, so this is the online learning section, and now we need to define what the weak online learner and strong online learner are. So, so the first obvious thing to do is just to copy and paste what happened in the batch setting. So which is exactly written here. It's exactly the same as in the batch setting. But then it turns out that this assumption is too strong. And the high-level idea is, the intuition is that in the early stage of online learning, you just cannot expect to get any kind of accuracies. You need to make some mistakes before actually learning something. So to encode this intuition, we propose something called the access loss, which is a constant. And we allow the number of mistakes made by the weak online learner to be x more than what happened in the batch setting. So remember, this s is basically the number of mistakes that you need to make before learning anything. Okay, and for the strong online learner, it's the same thing. We define it in a similar way. So it's basically epsilon times t plus another access log s prime. Yes.
So typically in online learning, do you see all the labels, all the data that pass through, or just some of the labels?
Let's assume you see all the labels. So after you make a prediction, you see the label. Okay. And okay, so this is our definition, and our result is that similarly in the batch setting, if you give me a weak online learner A, then again by using several copies of it, I can construct a strong online learner A prime. Yes.
So are you thinking of S as something that is little of t?
Little of yes. In fact, you can think of it as 1 over gamma.
So, okay, because so I was gonna ask, why can't you just think of pulling S in, pulling basically S over t inside and just thinking of it as gamma prime, right? So you just get a smaller gamma due to it. So why do you need to separate S? I guess maybe I'm not seeing that.
But this is a constant, so.
Is this for all big T? Are you quantifying over big T here? I guess like.
Oh.
Yes, all big T. Yes.
I see. Okay.
Yes. Right. So yeah, and actually this assumption is very natural. It's basically equivalent to Sorry.
So the weak learner has to keep doing well even as the examples get harder and harder, right? Because each round of boosting, examples are getting harder. You're getting to the more difficult cases.
You're getting.
Batch one.
No. In this one, in this case, it's just like any batch of. It's just for this sequence of examples, you need to do this. There's no weighting here. So there's no weighting on the examples.
Maybe my question is about the batch version. For the proof to go through, is it true the weak learner, it still has to be doing well, or at least better than random, even as examples are getting harder?
Yes, that's right. That's right.
So is it okay if it's getting if gamma's getting a little bit smaller and smaller?
But it has to be bounded from 0. So as long as it's bounded from 0, then you're fine. Okay, so so I was saying that this assumption is actually basically equivalent to what's going on in the batch setting. So it's a natural and mild assumption. Okay, so now let me tell you the high-level structure of our algorithm, of our online boosting algorithm. So as I mentioned, we will maintain several copies of these weak learners. And upon seeing example x1, what we will do is to pass this example to all these weak learners and then collect their predictions, these y-hats. Okay? And after that, we will construct our own prediction y-hat1 in some way that I will specify later. And after that, we see the true label y1. So this is the prediction phase. And then we need to do some update. So what we are going to do is to, for each weak learner, we will compute a sampling probabilities. And with this probability, we pass the example along with the true label to the weak learner so that it can do whatever it needs to do. And with the other one, with 1 minus p probability, we just don't give any feedback to this weak learner. Okay, and we do the same thing for every weak learners. So this is the update phase. And so this is 1 hour. And then for the second example, we do the same thing. We pass the example to the weak learners, collect the predictions, construct our own predictions, and then do some updates. Okay, in fact, we do this for every example. And now it remains to specify how you come up with this final prediction and how to compute these sampling probabilities. Yes?
I think, did I hear you right that you only pass the example to a weak learner with some probability?
Yes.
Why is that? Why don't you always pass it?
Well, you can think about it as putting some weighting in the example. So doing this is like you are putting the example a weighting of p to this example, meaning that how important this example is to the weak learner. It's the same thing happen in the batch setting. You reweight example so that difficult one get more attention. Similar here. Okay. And okay, so before I tell you our yes.
You can literally do weighting instead of sampling, right?
Yes, you can do that. Yes. And okay, so to measure, so before I tell you the details of the algorithm, let's see how we measure an online boosting algorithm. So basically, we are interested in two things. First, how many weak learners n do we need to maintain? And second, how many examples t do we need to see until before we reach epsilon error rate? And here are the results. So we propose two algorithms. The first one is called online BBM. And the number of weak learners that it needs is 1 over gamma squared times log of 1 over epsilon. So remember, gamma is the edge of the weak learner, and epsilon is the target error rate. And the number of examples is larger, it's 1 over epsilon times gamma squared. So is this good or bad? It turns out that it's optimal. So we show a Mascon lower bound, which means that you need at least this many weak learners and at least these examples to achieve epsilon error rate. So it's an optimal algorithm. You cannot do better. But this
Is there a trade-off between those two?
Well, maybe, but I mean,
If I have more examples, could I get away with fewer learners?
no, you cannot. You cannot.
So you also had the S prime, right? So S prime still stays constant. S prime does not end up being a function of t or n.
Think about S as 1 over gamma. Oh, S prime.
S prime.
S prime, yes. S prime. So if you think about it, when t is large enough, S prime over t is going to be epsilon.
Okay.
So we want to make that to be epsilon too.
Okay.
Yeah. Okay. So the problem of the first algorithm is that it's not adaptive. So the easier way to think about it is that it requires knowing gamma as a parameter to run the algorithm. But a deeper issue is that sometimes one weak learner can be doing much better than the other, but this algorithm is not taking the advantage of this. It's not exploiting this effect. So we want to do something similar to what the well-known adder boost algorithm does, which basically do a weighted majority vote of the weak learners. And so we propose our second algorithm. It's called adderboost.ol. And in terms of the bound for n and t, is unfortunately much worse. But the thing is that it's an adaptive algorithm. It's basically parameter free, and it can exploit the fact that some weak learners are doing better than the others. Okay. BBM stands for boost by majority. So the algorithm is taking a simple majority vote.
So that's kind of counterintuitive, right? I mean, you think that the ability to adapt to the weak learners improve your ability to learn rather than make it less optimal.
Well, I mean, our optimal goal is to get both optimal and adaptive algorithm, but we just cannot do this at this point.
So I guess like is the intuition that because so is the source of inefficiency the fact that you don't know gamma, or the fact that you're adaptive? See, he's doing two things at the same time. He's adapting,
Yes.
and as well he doesn't need to know gamma. And since you know less, you can expect to be doing worse, right? Like adaptivity probably is
Yes.
separate, right?
Yes, that's right. Yes. Okay, and compared to the previous work by Chandler, it's neither optimal nor adaptive. Okay, so now I just want to briefly mention the details of our algorithm. So the first one is online BBM is derived by generalizing something called drifting game. It's a game theoretic framework, but I'm not going to talk about it. But the algorithm is the following. So for the prediction, you just take the majority vote, as I said. And for the update, the probability of sending an example to a weak learner is proportional to the probability of seeing some number of heads in some number of flips of a biased coin. So you might think this come out of nowhere, but if you look at the game framework, it actually has some nice minimax explanation. So this is our first algorithm. And our second algorithm is derived from a very different perspective. It's using some sort of
What's K?
What's KIT?
K is something depends on some other quantities. It depends on how other algorithm is doing, basically.
So it's some kind of like running average or running.
It depends on the prediction of the previous weak learners, basically.
Previously.
Yes.
Learners.
Okay, and so this algorithm it predicts by taking some sort of weighted majority vote, and the update the sampling probability is some derivative of a logistic loss at some point. So I'm not going to go into the details. So these are our algorithms. And finally, I want to mention some empirical results of yes.
So going back
Okay.
to the previous case, so can I, in general, not think of, so once I think of sort of having these weak learners as my ensemble, then can I so where does it go wrong if I try to think of just running an arbitrary experts algorithm on top of it and using that to combine the prediction? And now I don't know how exactly to arrive at probabilities to send examples to these learners, but is there a way to actually utilize the existing experts algorithms? And in particular, I'm curious if the AdaBoost version already looks like using some existing expert algorithm.
That's right. Let's see. So in the original version of our algorithm, we actually use an expert algorithm to combine the prediction. But then we figure out a better way, basically, to just do an online gradient descent, which turned out to be better, to give you a better bound. Yes. Yeah, but that's a good point. Yes.
And the gradient descent is being done similarly on exponential loss or something, or?
What do you mean by exponential
Oh,
loss?
it's on logistic loss?
Yes, it is on logistic loss. Yes, it's a one-dimension. It's actually a one-dimensional online gradient descent. Yes. Okay, so we actually implement the algorithm in the open source toolkit RoboRapid, and so we try a bunch of benchmark data set. So for the weak learner, we just use the default learning algorithm in VW, but it's actually a rather strong one. So although we call it weak learner, and we compare 3 boosting algorithms. The first one, the two by us and the one by Shenandoah. Okay, and here the blue edges are the one with the best results for each data set. And as you can see, as the theory predicts online BBM, which is an optimal algorithm, when you try to tune the parameter, the gamma, to the best, then you get the best results. And yeah, so the improvement is not too big compared to the weak learner, but as I said, the weak learner is already quite strong. Is which error? Is the progressive validation error? Yes.
So at the beginning, you said there were some heuristic online boosting approaches.
Yes.
I'm not familiar with those algorithms. Have you looked at them closely, and do you have a sense of how they would compare with online BBM?
We actually didn't try that, but I don't think the setting is the same. I just don't think they work in the similar way as these algorithms.
So the way, how do you set the gamma? Like you just said gamma essentially equal to what you see on the left-hand side? Or no?
Gamma, no. You
Use tuning.
use a twin gamma,
So
yes.
you just kind of tune it. So it's not actually.
Yeah,
So it's just a hyper parameter. So it's not really like the.
yes.
And how, like, on average, do you have a sense of how big n ends up being?
I think in this experiment we use like 100, like 50 to 100 equivalents. Yes.
Could you formulate a kind of standard experts algorithm and compare to that? Like every weak learner is an expert and just do a standard exponential weight.
Oh yeah. Actually, I'm going to talk about it in the next part of my talk. But in that case, you are just you basically you only try to find the best expert in those weak learners. You are not improving upon those weak learners. While here, you want to largely improve upon each weak learners.
At least that, well, the theory says that, but you could still, I'm just wondering if it would just perform really badly or
Well, let's see. First of all, you still need a bunch of experts, right? What are those experts? So here we have a single algorithm as the weak learner. But if you want to do expert, so you're saying that to treat each weak learner as an expert.
exactly.
I see. I'm not sure. I don't think you can do better than any single expert, which is a weak learner in this case. That's usually the case in the expert algorithm,
Yeah, you
right?
can't prove you would do better, but
So I think the best expert would be the first weak learner, which would be exactly the BW baseline.
okay.
Yeah. Yes.
How big are these data sets in terms of number of examples typically?
How large are they? I think they range from like several hundred to several, like maybe 50,000, something like that. Yes.
I guess there's also a different distinction between, this is the way I think about kind of these weak learners and experts, is that expert given is more like an output of a weak learner, right? So weak learner given a data set will at least in the batch setting, right, will output many different classifiers depending on what the data set is, right? Whereas an expert, I think of typically as a classifier. So it's slightly
Like money,
Yes.
money in the email. That's an expert.
that would be an expert.
Yeah.
But weak learner would be more like, okay, pick one word, and if that word is there, then say it's a span. Okay, and it can look at the data and pick the best single word rule. I think that's at least the sense in which I think Haipeng is using weak learner,
Yes.
right? So that's why he can use VW, many copies of it, right? And still get something out of it. Out of using many copies of, say it's a span, if there is money, you don't benefit out of having 10 copies or 20
Well, no,
copies.
you would have
right?
to use different words.
Yeah, exactly. So.
Was there a question? Or?
Automatically.
Did you do any experiments with actually weak learners?
Oh, we did that for a regression setting. So we kind of generalized this to also to a regression setting, and we tried two other weak learners like one layer neural networks, and also this is let's see, a regression stem. So it's a regression tree with like height 1, and the improvement is much larger. It's like 10% improvement. Well, here you see like it's only like 1.5% improvement. So, any more questions before I move on to the second part? Okay, so now I'm going to talk about what you guys already asked about. It's on combining expert advice more efficiently. And this is mostly joint work with Rob. So what's an expert problem? So suppose you need to make some sort of decision every day. For example, which stock to invest in or which route to drive home. And you're confused, you are not sure how to do this. So you ask a bunch of experts. And these experts can be your actual financial advisors, or they can be something more abstract. They can be the path from your office to your home, like Route 1, 206, I-95. So, and the advice from these abstract experts is just basically saying that pick me. Okay, and another question is how to combine the devices and make smart moves in this situation. And so you guys already pointed out that there are some similarity between these two problems, but the difference are also there are also some differences. So first, in online boosting, we have a single weak learning algorithm, but we use several copies of it in different ways. While in the expert problem, these experts can be totally different. They can be totally different classifiers or something like that. And we do not assume any connection between these experts. And second, in online boosting, we assume that the weak learner has some edge. Okay? While in the expert problem, the devices from these experts can be basically arbitrary. There's no assumption at the device at all. And third, in online boosting, instead of, besides of combining the prediction of the weak learners, we also need to figure out how to control the inputs to the weak learners, to what kind of feedback you want to pass to the weak learners. While in the expert problem, it's purely about how to combine those devices. And finally, in online boosting, we aim to largely improve upon every weak learner, while in expert problem, it's more about finding the best expert in hindsight. Okay, so these are the differences. And why do we care about this expert problem? Well, for the first thing, it has many real-life applications that I already mentioned, some of them. And more importantly, it's also the foundation of many other learning algorithms. For example, batch boosting, bandit problems that are useful for advertisement placement, and also solving a semi-definite program or online principal component analysis. So these kind of things, they all use the expert algorithm as the meta algorithm. So this is actually really one of the most fundamental problems in online learning. And the formal setup is the following. So at each day T, you design a distribution over the experts. That's how you combine these experts. And then after that, the adversary or the environment reveals the logs for each expert, let's say LTI, for expert I. And at the end, the player suffers this loss for this round. So this is actually just the expected loss if you follow these experts according to this distribution BT. And we care about something called regret. So the regret to expert I is the difference between my total loss and the loss of expert I. So this is basically measuring how much less loss I would suffer if I would have follow expert I all the time. Okay, and the goal of this problem is to obtain sublinear regret to the best expert, which is the expert with the smallest total loss. So if my regret is sublinear, it means that on the average, I'm doing almost as well as the best expert. So even in the online fashion. Okay, and more generally, you can also think of comparing you to the top 10 experts, or really just to any combination of the expert. Okay, so this is the setup, and so there are many algorithms to achieve sublinear regret. But beyond the classic regret notion, people have also been thinking about some more difficult objectives. For example, how can you achieve much smaller regret when the problem is somewhat easy, while still ensuring worst-case robustness? Or how do you learn with unknown or even infinite number of experts? And how to compete with a sequence of different competitors instead of a static fixed one? And how to learn with experts who not only provide advice, but also provide confidence on those advice. So I'm being a little bit vague here, but the point is that all these things they were kind of studied previously to some extent, but with different algorithms. And our work is about one single parameter-free algorithm that can achieve all these goals, and in some cases also with improved results. So this is the main contribution of this work. And now let me just tell you how did we come up with the algorithm. So the main technique is to somewhat reduce the problem to a drifting game. Again, so I mentioned drifting game briefly in the first part, but it turns out that you can also use it here. So again, I'm not going to talk about drifting game, but the consequence is that it gives you a principal way to design an expert algorithm. So at the end, it boils down to finding an upper bound of some 0-1 loss. So here is an example of a 0-1 loss. And if you give me a convex upper bound of it, then I can, using this framework, I can give you an expert algorithm with the regret guarantee. Okay, so here are a few examples. So one of the most natural choice to use the exponential function as the convex upper bound of this 0-1 loss. So it turns out if you do this, the algorithm you get is exactly the exponential rate, saying that the weight to exp I should be proportional to some learning rate eta times the regret of I up until this round. Yes?
What is the x-axis on that?
The x-axis is basically the regret.
It's the regret, and that's the loss, the y-axis.
It is some function, some potential function. It's only used for the analysis. So I'm not writing the exact potential function here, but it just boils down to this problem. So is that clear, actually? Okay.
You can go on.
Okay. So yeah, so this is the most classic algorithm for this expert problem, and the regret you get is, let's say if you want to compare to the top epsilon fraction of the experts, then the regret is like square of t times log of 1 over epsilon. But so this is optimal, but the problem is that in this algorithm you have a learning rate eta to turn. And in fact, if you want to get this bound, eta has to be turned in terms of epsilon, so which is not parameter free and is not adaptive in this sense. And now, so what kind of other upper bound you can think of? Well, you are probably thinking about like hinge loss. So it turns out that hinge loss will give you linear regret, so it doesn't work. But if you use squared hinge loss, just take the square of the hinge, then you get something very simple like this. And it's actually very similar to something called the regret matching algorithm in the game theory community. But the point is that it's parameter free. You don't see any learning rate in this algorithm. But the bound you get is square of t over epsilon. So it's like much worse than the optimal. And now the question is whether you can get both optimality and adaptivities in one single algorithm. So it turns out the answer is yes. So we found this not so common loss function, which is like the exponential squared hinge, something like that. So you get this algorithm, looks complicated, but it's really not. I mean, there's no parameters here. It's parameter free. And the bound you get is almost optimal. You just have an actual log t term, which is super small. Okay, so you have an almost optimal algorithm and parameter free. Okay, so in a word, we have this through this game theoretic framework, we have a principal way to design algorithm, which not only recovers previous algorithm, but also give you one new algorithm that's both optimal and adaptive. Okay, so still this is not the end of the story. So I'm rewriting the algorithm here. We call it add the normal hedge for some reason. And so the regret is of order square of t. But so it's always increasing in t, which is not good because imagine a situation where there's clearly a good expert which is doing much better than the other. And you should expect your algorithm just to quickly spot this expert and just follow this afterward and incur no regret. So it should not increasing in t in that case. So So this one is too conservative. So, it turns out that we can do just a little trick to this algorithm. So I don't want to go into the details, but at the end, it gives you a much more adaptive algorithm. For example, you will get a smaller regret when the best expert itself has a small loss. And also, your regret is going to almost be constant when you assume your losses are generated in some stochastic way. So usually, as I said, we don't make this kind of assumption, but if you do have this assumption, the regret is going to be a constant. Okay, and it also resolve some open problems. And so now I want to give you one concrete example to show you what kind of improvement you can get when you use our new algorithm. So here's the application. So imagine you are given a very large unpruned decision tree. So a decision tree is just a tree with a different kind of question in the node. And when you have a new example, like an image, you start from the root, test the answer of the question, and depending on the answer, you go either left or right until you reach a leaf, which will tell you the label of this example. Okay, and so it's a very just natural and classic learning algorithm. But you don't want a super complicated decision tree because it will overfit your data. So you want the pruned tree, which is basically a subtree containing the root. Okay, and the goal here is that given this overcomplicated tree, can you predict almost as well as the best pruned tree in an online fashion? Okay, and notice that this is not even an easy problem if I give you all the examples and all the labels. And now, let alone we want to do it in an online fashion. But it turns out that these people found that you can reduce this problem to an expert problem, where basically each edge is an expert. And after you do this reduction, now if you apply our new algorithm at a normal hedge, you will get a parameter-free algorithm, and with exponential regret improvement. So the improvement mostly comes from the fact that our algorithm doesn't even need to know the number of experts, which is the number of edges in this graph. So the regret is also independent of that. So this gives you some exponential regret improvement. So this is the second part of my talk. Any questions? Yes.
So you mentioned that one of the reasons why experts is an interesting framework is that it feeds into a lot of other learning problems, like partial information, for instance. So I'm curious, does this also sort of lead to better bandit algorithms, for instance? And in particular, can you, so there are other parameters that you have to worry about there, like minimum exploration probabilities or and so on, and can you be more adaptive to those things too?
Yes, that's a very good point. We actually thought about that for quite some time, but I actually don't have an answer for that. So the thing is, we don't even know what the right bound is in the bandit setting if you compare yourself to the epsilon fraction of expert. So should you get like square of t over epsilon? It's not clear.
You just worry about regret to the best?
Regret to the best, and still there is some difficulty to like directly apply this algorithm in that problem. So yeah, we want to solve that, but we still haven't have an answer. Any more questions?
Questions about the first part.
The first part, okay.
Can you put up a slide with the results again?
Which slide?
The slide with the results.
The result, okay.
VW.
Okay, let's see. Yes.
Yeah. So did you say that to get that second column, you had to tune gamma somehow?
Yes.
So do I understand correctly, this is not really a fair comparison to VW?
Why is that? No, we also tune the parameter for VW.
Okay, so you have some sort of external pass over the private parameters.
Yes.
For both.
Yes.
Where you don't touch the test. Fine. So does this suggest then that when people really want to get the optimal predictor, that whatever they're doing with VW, they really should put online BBM on top of it?
Well, I'm not sure about it, but I mean, so one thing is that you need to tune parameters, right?
I suppose you have a lot of computation. You can use a lot of data.
Yeah, I mean, I think so. You should at least try this to see whether you can get better results. Yeah.
So I guess it seems like even your adaboost.ol, which is parameter free, seems to at least improve upon the baseline always, even if it's not improving as much as online
Yeah.
VM does, right?
That's right.
So
Yes. Yes.
The baseline is an online version of VW or
Yes.
batch?
Online. So VW is online by default, right? Yes.
So what's the learning algorithm that's used by default? It's just
It's a little bit complex. It combines the importance and variant update, the autograd update, and the normalized updates.
So you in order to run these other versions, you first tune VW,
Yeah.
and then you use the tuned VW as a weak learner?
Let's see. I think we first tuned the VW and then we just used the best learning rate for the weak learners. Yes. Okay.
and you're saying that this new algorithm is already available in VW.
Yes, it's already available with this comment.
Default setting
Yeah.
to improve results.
Because if it's just the learning rate that you tune, you might be able to. Okay, we can check it out. Yeah, but you can.
Okay, so let me go back. So, okay, so now I'm going to talk, briefly mention the third part of the talk. So this is actually done when I was an intern in this lab. It's done work with Eric, Nicholas, Bianchi, and John. So it's about how to get efficient second-order online learning via scheduling techniques. So let me just first give you a little bit background. So imagine you do a very simple online linear prediction. On each round, you see an example xt, let's say an image. And you do linear prediction. So you maintain a weight vector, WT, and you take the inner product of the weight vector and the example. And depending on the sign of this, you predict whether the image contains a cat or not. Okay? And after that, you see the true label and suffer some loss. And you update WT to a new weight vector, WT plus 1. So it's just a typical online learning setting that I have been talking about. And now if you look at how do we usually update WT? Well, the most classic algorithm is the online gradient descent by Zingovich. So it's basically the same thing as gradient descent. You just move in the opposite of the gradient direction, scaled by some learning rate eta. So GT is the gradient. The detail is not important, but this is the algorithm. So it's a very efficient algorithm, but there's some problem. So the problem is that the performance usually depends on the representation of the data, or more formally, the conditioning of the data. So here I'm giving you a two-dimensional example. So on the left, we have a data that's considered as well conditioned. So each point is a data point, and if you look at the overall shape of this cluster, is spherical. So meaning that there's no, each direction in this data is more or less the same. Okay, and this is what we consider as well conditioned. And on the right, I have a data set that is considered as ill conditioned, where you can clearly see this one direction that's much larger than the other. Okay, and so we have a formal way to compute something called the condition number, which measure how well conditioned the data is. Okay, and the thing is that as you can guess from the name, we like this kind of data, but not this. And why is that? So if you look at this simulation, so we first generate a set of data in some random way. And then, based on this data set, we generated 20 more data sets by changing the representation of the data, of the features, but keeping the same labels. Okay? And this data set, they range from this kind of spherical data, well-conditioned data, to this kind of scale data, okay, as the condition number increases. But keep in mind that essentially they are the same data set. They are generated from the same data set and they have the same labels, okay? And you really should expect that the algorithm is independent of how the data is represented. But in fact, if you look at online gradient descent, this is the error rate on this 20 data set. It's basically increasing linearly in terms of the condition number. So it's good. So it's bad. So we only get good accuracy when the data is well conditioned. But the nice thing about this algorithm is that it's very efficient. In fact, the time for each example is of order OS, where S is the sparsity of the data, how many non-zero you have in the example. Okay, but now the question is, do we have an algorithm that's independent of the representation of the data? And the answer is yes. It's driven by something called online Newton by Hazan et al. And so the difference compared to online gradient descent is that you have have a condition in front of GT, the gradient. So this AT is basically the sum of all the outer product of all the previous gradient, and you take the inverse as the conditioner, and it has some connection to the Newton method, so it's called online Newton. And if you look at the performance, it's completely independent of the condition number. So you get the same error rate no matter how you transform the data. So this is what we want. But the problem of this algorithm is that the running time for each example is O of D squared, where D is the dimensionality of the example, which can be several millions for high dimensional data. And you cannot improve it even if the data is sparse. So you just have no way to run this algorithm when you are dealing with high dimensional data. Okay, and can we do something between? So you might have also heard about something called addergrad by Ducci et al. So it's basically saying that if we can't afford to do the whole matrix, what about we just take the diagonal? In fact, they are doing the square root of the diagonal for some reason, but that's not important. But the thing is that, so this is a very efficient algorithm. You still get the same capacity as the online gradient descent, but the performance, it improves upon online gradient descent, but it's still increasing very fast as the condition number increases. So now the real question is, can we do better? So here's what we propose. So if you look at this plot, the performance is much better. It's still not independent of the representation, but it's growing much slowly. And so the idea of the algorithm is that if you can't afford to do the full matrix, how about you just do a sketch of the matrix? So a sketch of a matrix is basically a simple matrix that approximates AT well. So you can think of a simple as of low rank. Okay. And so we call our algorithm sketch online Newton. So the efficiency of the algorithm is the following. So here M is the size of the sketch, which is you can think of it as the rank of the matrix. And the running time is like M S plus M cubed. So here, in this example, M is 10. So I only care about, I use a rank 10 matrix to approximate my full matrix. And so it's 10, and even 10 cubed is not that big. And in fact, we can also improve this to M squared, but it's not important. So it's basically just M times slower than OGD and undergrad. But you get a huge improvement in terms of error rate.
So what's the relationship between M and D?
M is much smaller than D. Yes, that's a good question. M is much smaller than D. So in practice, we expect M to be like 10 or 20, something like that.
So you actually try this on some high-dimensional problems and found it.
Yes. Well, this is not, this simulation is not too, it's like maybe 10,000. D is 10,000 in this example. Okay, so I don't want to go into details. I just so the challenges in this work is that you need to show that after using sketching, the performance of the algorithm is not too much affected. And second, you need to show a very efficient way to implement the algorithm. And it's not clear at all, because even if you can do the sketching efficiently, you still need to take the inverse. And then you need to do it in terms of sparsity instead of D. So there's some non-trivial thing happening here. But we give some nice solution in this work. So let me just conclude here. So I talked about three things: online boosting, where we propose a new framework and some optimal and adaptive online boosting algorithms. And the second thing is about combining expert advice. So we have a general principle way to design this algorithm, and using this we get an adaptive algorithm with many desirable properties. And finally, I talk about briefly how to use sketching techniques to deal with ill-conditioned data in the online learning. And I just want to mention something that I'm excited about and want to work on in the future. So the first thing is to move to non-convex models. So we know a lot of things about convex models and convex optimization in machine learning, but a lot less in the non-convex area. But also we have seen a great success by using non-convex models such as deep nets. And there are certainly a lot of things to work on in this area and a lot of mystery to solve. And also, machine learning is more about a continuous optimization at this point. But on the other hand, some problems are just better modeled as a discrete problem. And some modular optimization gives some nice solution to this issue. And it also builds a bridge nicely from discrete optimization and continuous automation. And I think this is something that we should pay more attention to in this area. And finally, machine learning algorithms are also too focused on currently are too focused on solving one single task. So you build one system to solve one task, and you build another system to solve another task. But sometimes these tasks, they just have a deep connection between these, between the problem. And you kind of want the system to automatically recognize this pattern and somehow learn from each other. So multitask and transfer learning gives some intuition, gives some insight to this issue. But I think this is a very difficult problem, and it's really a long-term direction that we need to work on. And that's it. Thanks. Questions? Okay, thanks.